So the first thing that we're going to do is we're going to go back and we're going to draw a heating curve. So kind of like the one that's right up here above, if you remember doing those. I want to make it big enough, though, that I can write some words on it. So make it maybe half of a sheet of paper or so. And remember, a heating curve looks like this, roughly speaking. Remember we said that right here it was a liquid, or no, sorry, it was a solid, right? It's a liquid here, and it's a gas right there. And then what's taking place in these two places? Anybody remember? That would be about 0, what? Yeah, melting and freezing, and then vaporization and condensation. They're your phase changes. So temperature is over here on the left in degrees Celsius, and then I guess basically time would just be on the right. Doesn't really matter on the x-axis. Okay, so with this, remember we said temperature is changing any place that it has a positive slope, right? So, yeah, the temperature can go up for a solid, it can go up for a liquid, it could go up for a gas, or it could come down. Remember, during the phase changes, the temperatures didn't change. Okay? We have been using, where to go? We've been using this equation right here, right, to solve different things. We can apply this equation to this chart. But there's a small problem. If I try to use this equation right here where the temperature doesn't change, and the temperature change is 0, what would that do mathematically to my Q? Make it 0, wouldn't it? Because if I multiply all this stuff by 0, then Q becomes 0. And that's not what I want. I can't do that. But in these places right here, when it's a solid, I can use this equation when it's a solid because the temperature does change. I can find the specific heat of water. I can find the mass of water. Same thing goes right here for a liquid. I can use Q equal to MC delta T for a liquid. And I can also solve Q is equal to MC delta T for a gas. It'll be just like our old problems. The problem is this. I need to be able to figure out here. We melted ice in class, right? Well, we had to apply heat to it to melt it, to speed it up. So clearly, like, there has to be heat involved in these processes. So we have two new equations that are on your reference table. For right here, I have Q is equal to mass times H sub F. And I'll explain what that is in just a minute. And then for the top phase change, I have Q is equal to mass times H sub V. Right down here, I can explain. Q is equal to M times H sub F is used for melting and freezing. Now here's what I think is crazy. The F does not stand for freezing. Just to make chemistry a little extra confusing for you, the F actually stands for the heat of fusion. And in this case, they use fusion to equal melting. Is that nice and confusing to you? You also have in your notes, if you go back and look at those, you have delta H solid. What that stands for is freezing, solidification. Which makes sense that when something freezes, it solidifies, it becomes a solid. Something that will be helpful to you to know is that whether you write the delta H of fusion as H sub F, so H sub F, or delta H fusion, those are equal to a negative value for the delta H of solidification. That sounds like a mouthful. Not as bad as it sounds. Basically what I'm telling you is that if the heat of fusion, if it takes 10 joules to melt something, then that means that you will need to take away 10 joules in order to freeze it. Remember what we said a while ago, that positive delta H values mean it's going in and negative means it's coming out? Same way here. A positive number means I'm heating it up, and a negative number means I'm taking away heat or I'm cooling it down. Because all you get on your reference table is this. So I can work this for freezing too. I just need to make that a negative H of F. Same thing here. H sub V stands for vaporization. Well, what's the opposite of vaporization? It's condensation. So by the same token, if I have a delta H or an H of vaporization, I can turn it into the opposite process by just making it negative. If it takes 52 joules to heat it up to vaporize, then I have to take out 52 joules to make it condense. Your reference table has these. You've just not paid it any attention. Look right here. Do you see heat of fusion of water? They give me a number. Which means if it takes this much to melt it, then it's negative 334 joules per gram to freeze it. Here's the heat of vaporization of water. It takes negative 2,260 in order to cool it down and condense it. But you only get the positive numbers. It's up to you to make them negative. So, all right, that's a lot of info. Let's put it to use and see if it makes some more sense seeing it worked. I'm gonna leave this here and I'm gonna come back and forth to it. So here's my first problem. Okay, this one is the most simple way that something is going to be worked. Okay, it says how much heat is required to raise the temperature of 789 grams of water from 25 degrees Celsius to 70. It's your problem number 1 on your worksheet. I changed it from ethanol to water. So you don't necessarily have to rewrite it. You can work it right on the page. I also changed the 70 to 70 decimal to make our sig figs a little less yucky. Okay. First thing I need to do is I need to look here. 25 to 70. If it goes from 25 to 70, isn't it changing right here in this liquid phase? Am I going through any change of state whatsoever? Nope. Then what that means to me is I can work it with one of these Q problems. The thing that I'm going to have to memorize for the test is when can I use the Q equals MC delta T and when am I going to have to use the other two equations. The other two are for phase changes. So I can plug this into Q is equal to MC delta T. What's the mass of my water? 789. Okay, my C. Remember from before, we had this list up there, and like we've done this before. I'll put it up here, so if you watch it later, you could pause it if you need to. Remember, C is specific heat. Well, my reference table gives me a whole list of specific heats of water. Which one should I choose? Ice, steam, or liquid? Liquid, yeah, because it's a liquid at 25 degrees Celsius. So I'm going to pick the 4.18 joules over grams degrees Celsius. And then my temperature change, remember, it's from the final temperature minus the initial temperature. So this one's going from 70 to 25 degrees Celsius. And if I stop and I do my numbers for that, I've got a pretty big number there. It's going to have 3 sig figs. Remember, this doesn't count, these count, and this one counts. This is a reference table number. We're not counting reference table numbers. They have an infinite number of sig figs. These both have 2. Like when I subtract 70 minus 25, it becomes 45, correct? That's a 45 degree temperature change. That's 2 sig figs. This has 3. So my calculator says 148410.9. I get to keep those first 2 digits. And not only that, it's large enough I should really put it in scientific notation. So that's 1.5 times 10 to the 5th joules will be my answer. Takes quite a bit of heat to raise it up 45 degrees Celsius. Now, my next kind of problem gets a tad more complicated. Look at my second question here. This one is asking me how much heat is released when 432 grams of water cools from 71 to minus 18. Well, I need to figure out if I have a phase change in there. And if you want to look at this, if I go from 71's up here in the liquids range down to minus 18, am I going to go through a phase change? Which means I can't work the Q equal MC delta T during the phase change. This is actually going to end up, like I can work one problem from 71 down to 0. So I'm going to work one problem going from 71 degrees Celsius to 0 degrees Celsius. Then I'm going to have to work a different equation as it freezes, because I can't use the delta T of 0 or I'm going to get that there was no heat involved. So I'm going to have to work another one for freezing. And then once it gets it down to 0 degrees, it's going to drop it all the way down to negative 18. So I've got 3 problems. I know you're excited. So here, as long as I have a temperature change, I'm game for Q is equal to MC delta T, which means these two, old problem, one that I'm very familiar with. This middle one, though, is going to be the freezing one. So when you go to your reference table and you're trying to figure out which of these things do I need to use in order to figure out freezing, down here you have heat of fusion. It's kind of small up there, I know, but I see it. It's the HF. So I'm going to have to use that MHF one. I'm going to use Q is equal to MH sub F. Okay, for this part, the mass of my water is 432 grams. For my C, it's like we did before. I have to consider that there's three specific heat values on here. Which one is going to be the most appropriate for water at 71 to 0 degrees Celsius? Liquid one. So that's 4.18 joules over grams degrees Celsius. And then my temperature change is going to be 0 minus 71 degrees. And if you're thinking, but that's going to give me a negative number, yes it is, and it should. Because my question says how much heat is released. And haven't we been saying that a negative Q or a negative H value means heat is being given off? That makes sense. It should be negative. You do some number crunching, you will get, it's going to have 2 sig figs to it. I will get negative 130,000 joules. Now I'm going to keep that whole number right now, and I'm not going to do anything else with it, but just leave it. I'm going to save it for a minute. Go to my middle problem. On the middle problem, the mass of water is still 432 grams. My HF, I don't have to memorize, it's right here. But now, am I melting it or am I freezing it? So it's going to have to be negative. It doesn't make sense if I have one number that's negative and then another number that's positive and then back to another number that's negative. So it's going to be negative 334 joules per gram. That's going to have 3 sig figs. So it's going to be 144,000 joules. It actually takes it has to take out more energy to freeze it and not even change its temperature than it does to lower it 71 degrees Celsius. It's kind of amazing. This one, same deal. I've got 432 grams. Now, what state is it from 0 to minus 18? It's a solid, right? So I'm going to have to use the C value for ice, which is 2.05 joules over gram degree Celsius. And my temperature change on this one is going to be negative 18 minus 0. And that's right, because again, it'll give me a negative value, and I should. I'll have 2 sig figs again, so that's going to be negative 16,000 joules. Now, for those of you who are significantly figured challenged, I don't know, your sig fig challenge, that sounds better. If you're sig fig challenged, okay, I'm going to line them up with place values to do this. In order to calculate the total, I have to add them together. So that's negative 130,000 plus negative 144,000 plus negative 16,000 joules. Okay, so that's 29,000 joules. But the question is, where do I cut off my sig figs? Well, this one is precise to the 10,000th place, this one is precise to the thousandths, and this one is precise to the thousandths place. And our rule for addition and subtraction was it's the least precise. So the furthest one left is the 10,000ths place. Well, that means I get to keep the 9 and I get to keep the 2. I get to keep everything to the left of it. Well, do I have to cut anything off? No, there's nothing there. But it would be better to give it in scientific notation. So 2.9 times 10 to the 5th joules, and make sure that you put that it's negative. Or, like we said earlier, you could say 2.9 times 10 to the 5th joules were released or given off and omit the negative. But one way or the other, you got to show that it's given off. Now, there's only one more way to make it more evil. And it's to go from either somewhere here to somewhere up there, or somewhere up there to somewhere down there. But what would you do if you did that? How many problems would you have? 5. You would have 5 problems. You want me to work one that way? I've got yeses and nos. Do it. Gage says do it.
Okay, so basically, at the end of it, all you're going to do is add them all up.
Yep. Here, how about this? We'll pre-plan it, okay? Here's one. We can at least plan it. Calculate the amount of heat needed to convert 96 grams of ice at minus 24 to steam at 128. The main thing is you need to be able to recognize with any of these I'm going to give you whether or not it's going through phase changes, like when do I use Q is equal to MC delta T, when do I use the other Q is equal to MH something. Remember, as long as it's changing temperature, I'm good with Q is equal to MC delta T. So I like to pre-plan it and kind of figure, okay, minus 24 will have to get to 0 first in order to just reach the phase change, right? And it may help for you to draw something out like this. I've got to go from below freezing up to 0. And then it's going to have to melt. And then once I end up melting, then I'm going to have to go from 0 up to 100. So then that's going to be another problem, is 0 to 100 degrees. And then once it goes from 100, then it's got to vaporize. So that's going to be a second phase change problem. And then after it's vaporized, then I can start changing the temperature of the gas. So then I can go from 100 to 128. So yeah, now I have 5 separate sets of problems that I can work. So, and then I'm going to have to go back and look and see, hey, temperature change. That means that I can do Q is equal to MC delta T. Hey, there's another temperature change, so Q is equal to MC delta T. Same thing here, Q is equal to MC delta T. I don't see a temperature change with either one of those. Well, the one that I'm going to use for melting is Q is equal to mass times the heat of fusion. And the vaporization one, thankfully, is easier. It's Q is equal to M times the H of vaporization. And from there, this is the hardest part. The hardest part is planning out how many different equations that I need to work. So, if you want to, I'll pause the video there and we'll pause you there. And you can take a moment to, see, there you go. You've got the answer there if I get rid of that. So there is this. And then what do we say you would do with these at the end? You would have to add them up. And I don't currently have them up here added anywhere. What may hurt more people rather than not is the sig figs. So if we add up all of these, let's see. I don't remember what I got earlier.
You have a line over that 0 if you see.
Do what?
There's a line over that 0 if you
There is, yes, because that's significant, because this had 2 sig figs. So, and I put it in this one because when I go back and I consider place values, I need to remember that it's significant just in case it would change my answer. So, and if we need to discuss that, I mean, that's totally fine. Because I know somebody else has already asked about the sig figs in general. So let's see. On my paper, that comes out to be 302,100. But going back with sig figs, look, this is good to the hundreds, thousands, 10,000s, and 100. Well, which one's the furthest place value to the left? 10,000s? So that means I get to keep this 0 right there. But if I write it out as 300,000, that's not significant. It's going to have to be 3.0 times 10 to the 5th joules in order to make it significant. And I should put it in scientific notation anyway, because I've asked you that anything greater than the thousands place be put into scientific notation. Yes?
So this one's the opposite of the last one, and we want our answer to be positive.
Yes, this one is the opposite of your last one, and you want it to be positive, because if you look at it, isn't it warming up? Heat's going to have to be going in, so my numbers should be positive.
So our minuses should our minus signs should cancel out.
Yes, when you do your final minus initial, your negative signs, like your minus signs, should be turned into positives because I'm doing 0 minus negative 24. And that should be a sign to you because that's been our theme this whole way. If H is positive, it's warming up, heat goes in. And if H is negative, it's cooling down because heat's being given off. Yep. All right. I will finish this one up